Okay, it's 5 o'clock, so let's get started. I guess I have the fortune of having the closing talk for the day. So I want to welcome you all to Build. Thank you for attending my talk today. My name is John Falcons. I'm a program manager in Windows Device Connectivity. I also have with me here Peter Wieland in the front row. He's my developer counterpart in the hardware developer experience team. And today, as the title kind of indicates, we're here to talk about new support for low-power buses on Windows 8. So first, we're going to start off by talking a little bit about why we need low-power buses, why we are adding new buses at all to Windows. Then we're going to take a look at Windows 7 connectivity versus Windows 8 connectivity and the new options that exist. And then we're going to introduce each new bus. I'll explain that later. And then we're going to take the example of a sensor in our Windows driver kit and walk through how you would go about putting that sensor into a Windows 8 system end-to-end from both a hardware builder perspective and a software writer perspective. So why we're all here and what we're trying to do for Windows 8 and what I expect many of you are here to learn is how we can enable systems to reduce power consumption by using low-power peripheral buses. This topic is going to be familiar to you if you've ever worked building phones or tablets. And we've added support in Windows 8 we're trying to lower power consumption. So, why Windows needs more buses. For the purpose of today's talk, I'm going to group buses in Windows into 3 different categories: standardized buses, proprietary buses, and simple buses. Standardized buses are things like PCI and USB. That's what most users are familiar with. They have standardized connectors. They're very fast, very flexible. They can enumerate devices that are plugged in, so it's a very plug-and-play experience. And in Windows, there are no drivers from the user's perspective. It's all covered by class drivers. We next have proprietary buses. These are buses that really most users don't know about and really never need to know about. Think like SM bus, low pin count buses, various buses within the system that have proprietary uses, proprietary drivers. Windows doesn't do a whole lot of hand-holding there. There's really not much that the user needs to know about this. It's kind of invisible. And then this third category, which we've created to call simple buses. These exist inside your PC today, but they're often hidden behind a special controller or special firmware. And we're going to talk today about I2C, SPI, high-speed UART, and GPIO. And this is really this third category is where in Windows 8 we spent a lot of time to try to make the experience great for hardware developers, system builders, and end users. So looking at these simple low-power buses, Windows had a few challenges. As many of you know who've worked with phones or other tablets, there are many system designs and many form factors, lots of different wiring configurations, and there's just this whole ecosystem is about diversity and about flexibility. Peripherals may use several low-power buses rather than one. In the USB world, you think one connection, one device, whereas peripherals on low-power buses are going to usually require multiple buses that each have their purposes broken down by bus. We wanted to try to do what we could to make peripheral drivers portable, like they are on standardized buses today. And we really wanted to make sure that the power and cost savings, which are the main reasons we use these light buses, can actually be achieved. So our solution and what we're trying to offer you today as someone writing a driver on a simple low-power bus is you write the driver once and we take care of the per-platform configurations. The idea is you write your driver, we'll handle the plumbing, we handle all those complexities that each and every tablet, each and every laptop, each and every desktop will present. So I'm going to do a quick demo, and this is going to be really familiar if you've ever worked with maybe other embedded operating systems or mobile operating systems. A normal thing, a normal challenge is I have a part that I want to sell, and it gets connected differently. Maybe it has different configuration options. Maybe you're on different architectures, but basically you want to write a driver that has to work on multiple devices. So what I have here, let me switch over. I have two tablets here, one from our good friends at Qualcomm and one from our good friends at NVIDIA. Both of them have written bus drivers that I'll tell you a little bit about later for I2C GPIO. And my team wrote a simple accelerometer driver or a motion sensor driver based on the sample that's in the Windows driver kit. I'll talk about that sample more, but it took about an hour to modify it for this new part based on the data sheet. So you can see here, this is a very simple demo. What we have here is I can prove to you that the accelerometer is hooked up and the screen rotates. And I will show you the driver loaded in Device Manager. I can't promise fancy graphics today, I apologize. So we're going to scroll down to the sensor that you can see the Microsoft KX-TF9 accelerometer. Now, is this in focus at all or even visible? I will take a quick look. I'm sorry. Oh, goodness. Let me try to zoom in a little bit. And then the focus. Let me change that. So, sorry about this. It's these get a little different. Okay, close enough. So, what we have here is to show that I'm not cheating here. We have a Microsoft-written accelerometer driver running on the Qualcomm tablet, which is wired very differently from the NVIDIA tablet that we have right here. And the NVIDIA tablet also, I might have to do a different threshold. There we go. The screen rotates. I'm not making this up. We'll see in Device Manager. Uh-oh. Oh, there it comes. Sorry. These are all hand-built units, so touch tends to be a little finicky, especially during demos. Okay, here we go. You can see right there. I'll zoom in a little bit further. You can see right there, we have the same accelerometer driver. So again, we wrote one piece of code. We knew that we were a part that used I2C and a GPIO interrupt, and Windows took care of the plumbing, worried about the details that I'll show you in the coming talk. So this is what the inside of a Windows 7 PC might look like today. You have your system chipset on your motherboard. We have our various buses, PCI, USB, SM bus. And this is what the inside looks like both physically and if you look in Device Manager, this is essentially what your device tree looks like. You have all these buses which enumerate their connected peripherals, worry about the name, worry about the matching with drivers, configure all the settings, and it's pretty nice actually. But if we want to use low-powered buses and get the advantages there, hello? I think we have a clicker. There we go. So looking at the inside of a Windows 8 system with low-power buses, instead of looking like a tree, we look a little bit more like a spider web. As you can see here, we'll have multiple devices connected to multiple buses. GPIO is used by just about everything. And you'll have just a whole net of connections. And device enumeration is going to look a little different too, because we can't use this tree structure when in fact the physical structure is a bit of a web and there is no true parent-child. So device enumeration in Windows 8 for low power buses starts with firmware. Firmware is what comes from the system manufacturer and the firmware writers there. What they do is they write up how everything is connected. This is done through ACPI at ACPI 5.0. So they put everything in firmware, and we start with the firmware. And looks like my clicker has some reduced battery length. Here we go. So we start with the firmware, and we look at ACPI. And ACPI is going to go through and enumerate all of the controllers, I2C, SPI, UART, et cetera. We're going to find all the controllers in there. Generally, a system might have 2 to 6 of each type of controller. And then we're going to go in and enumerate your peripherals. This is all coming out of ACPI because these things aren't plug and play. So all of this is stored in the firmware of the computer system. Okay. So how do your drivers then go and find which controllers, which lines, which wires that you need to be using? We have this new component called the Resource Hub. And the Resource Hub is kind of like a digital matchmaker. And what that does is provide the connection pipes to each bus. So if you're the touch screen here, you start by asking the Resource Hub for, hey, give me my connections. I'm expecting an I2C connection and some sort of interrupt. Ask the Resource Hub, and the Resource Hub gives the connection link, and then you go and you start talking right to the proper buses. And we do this for everything. Again, I like to think of it as the digital matchmaker. It really, you don't worry about the netting and the piping underneath, and let the Resource Hub take care of that for you. So what are these new buses that we're supporting? Well, you've heard me mention them a little bit earlier, and I use the term new, obviously, with very heavy quotes here. These buses are not new at all. In fact, they've been around for 20 to 30, really, if you think of GPIO, forever. So we look at the 3 categories that we're introducing. The first is GPIO, or General Purpose I/O. That is used for just about everything, used primarily for interrupts or general I/O. In the general I/O case, you have your lights, your switches, your buttons, all the Windows buttons use GPIO. It's a wake source. It can be a power on-off for radios. It can be used for a lot of things. We also use it for interrupts, and that's really important. For all sorts of drivers, especially on these low-powered buses that don't have their own interrupts, you can use it for interrupts. SPB, or Simple Peripheral Bus, is the next group that we have, and that's I2C and SPI. These are used for just about everything, especially I2C. We've seen more interesting uses of I2C than, every day I learn a new way that I2C is being used inside a computer. So I2C is up to 3.4 megabits. SPI is really as fast as a chipset can possibly move, but SPI generally tops out around 160 megabits. And it's really used for a wide variety of peripherals. We've seen just about everything use I2C or SPI in some way. And then serial, you might be thinking, well, this isn't really new. Windows has had serial support for about 2 decades. So what we're really adding here is support for high-speed embedded serial. Most serial that people think of is the serial that's on the back, that little RS-232 port on the back of your PC. For today's talk, we're really talking about high-speed serial that'll go up to 20 megabits. We don't use COM ports because everything is soldered together. And radios are the biggest users of serial. I like to think this is not your grandmother's serial. So the APIs for each bus. GPIO, obviously we have new APIs for the general I/O aspect of that. For interrupt functionality, it's just the standard Windows interrupt APIs. For both user mode and kernel mode drivers, it's just going to look like an interrupt. There really is no new code for that usage. For I2C and SPI, we created the simple peripheral bus interface. Basically, it's very simple. It's as simple as the buses themselves. It's reads, it's writes. You can unlock and lock the bus, but it's very, very simple. And then high-speed UART uses the 20-year-old serial APIs that have done us so well for 20 years. But we've eliminated the use of COM ports because, as I said, there is no more COM5, COM7. Everything soldered in ACPI gives us the luxury of knowing what's connected to what. So how does this all come together in this new world? The chipset vendor who owns those buses is going to provide the bus drivers. The peripheral driver writer uses these new APIs and creates the peripheral driver. The system builder connects everything in ACPI, lays out, it essentially takes all the wiring and maps that all to ACPI. And then Windows helps to manage all of that plumbing so that you, the driver writer, just really don't have to worry about that. So the example we're going to use today is the accelerometer driver that's in the Windows driver kit. That is what you saw running here. For the purpose of the demo, we modified it to work with a Kionix part. The driver in the Windows driver kit works with an Analog Devices ADXL345 part. This is what it may look like in terms of wiring. I do want to put one little note here that while you see system on chip mentioned throughout this presentation, it's not limited to system on chip. These buses are obviously very prevalent on system on chip, ARM and x86, but also you're going to see these on all varieties of PCs that match the hardware specifications for these new APIs. So looking at how the SPB accelerometer sample is wired up, you have this part, this little accelerometer, which works on I2C or SPI. Really, the driver can work with either, but we use the example of an I2C with an address 1D and a GPIO interrupt. So this is what it looks like in wiring. This is a picture of the driver stack. That red box right there is the accelerometer driver. It implements the sensor class extension. So at the top edge, it's talking to the Windows sensor stack. At the bottom edge, it uses the simple peripheral bus, or SPB API, to talk to the I2C controller driver, which you don't have to worry about because that's come from one of our friendly silicon vendors. And then use regular interrupts for the GPIO. So what's the ingredients? I kind of just called them out there, but again, it's a user mode sensor driver. It implements the sensor class extension. It uses the SPB and interrupt APIs. And it's worth noting that it's a user mode. There's a variety of interrupts, but all kinds of interrupts are available in both user mode and kernel mode. This is something that you generally won't have to look at, but it's worth showing. So this is what the ACPI block looks like for that sample. You can see here, besides a lot of words, is that we have the name, the hardware ID is that first line. Generally, that's going to be something that looks like 4 letters and then 4 part numbers. Like, for instance, if it was an Atmel touch chip, it would be ATML1234. The class ID sensor, so that it appears in the right place in Device Manager. And then we have our 2 resources. In this case, if you're writing a peripheral driver, you're going to tell people that, hey, my part, I need an I2C connection, and I need an interrupt. And then based on the data sheet and the part information that you provide to manufacturers, they will put this in depending on how they wired it. A lot of I2C and SPI parts allow a variety of settings, maybe multiple addresses for flexibility, maybe multiple speeds. So this is where the system builder fills in this information. In this case, as I said, we're using I2C controller number 3 with an address of 1D running at 400 kilohertz. And then the GPIO, it's a level interrupt that triggers when the line goes high, and it's on pin number 19. So let me just page back real quick. So this is what the system builder would worry about, and then you, as the driver writer, We just worry about how the APIs, and you don't worry about this. This is done for you, and this is what this is us taking care of the plumbing. So what's in the Windows driver kit? I am here to plug the WDK here. We have a variety of tools. We have really spent a lot of time trying to put everything you need in the Windows driver kit to get going. So we have the SPB test tool, driver and application. What that is a simple peripheral driver that it's just a fake peripheral driver that loads on I2C and an interrupt. And you can use a command line application and kind of poke and send data and read data and just digitally prod at your device. The SPB accelerometer sample, which is a fully working sensor for that analog devices part, but really easy to modify for just about any sensor part. I don't want to be too bullish, but I think really it can be converted into pretty much any sensor in about a day. We have a Bluetooth bus driver on UART that there's another talk that I've linked at the end. We're providing support for Bluetooth on a variety of buses, but especially high-speed UART. That shows how the serial APIs and the serial use of the resource hub are used. We have a UART controller driver, which implements DMA and kind of shows what a new controller driver looks like. And that's something that you can install on your PC. And then SimDevice is a sample that shows usage of both GPIO, general I/O, and interrupts. So how to get started? And let me explain a little bit on number one. This deck was created with really with the foresight that you will be able to get your hands on hardware that has I2C and SPI and UART and GPIO, not today, but in the future. So what you can do is get started with the WDK, and that action item number one right here is something that you should stay tuned on the Microsoft website, and we will talk in the future, in the coming months, about how you can get your hands on ARM and x86 hardware that has all of these controller drivers done from our wonderful partners. So once we've gotten this hardware, which you cannot get today, you start by installing Windows and get your hands on the Windows driver kit. You get the platform drivers from the platform providers. So Intel, NVIDIA, Qualcomm, TI, AMD. You go to them. When you get that hardware, you go and install the controller drivers for your platform. Attach your peripheral. And this is really kind of I'm thinking this example is of an I2C peripheral. So you attach your peripheral and work with the ACPI. That can be with the person who provided the platform, or there's documentation in the kit about how to write your own ACPI if you just kind of want to throw your own blob in there and poke and prod at the plumbing yourself. Move over here again. Use the SPB test tool, which again, we provided in source. And what you do is you load that little fake peripheral driver up, make sure your ACPI looks good. You poke and prod at your device digitally, maybe write a few bytes, read a few bytes, check to make sure the interrupt is there. That way you know everything is wired up and good to go. And then take one of our fabulous WDK samples and you write your driver. We've really tried to make it as easy as possible, and I really have to emphasize that the Windows driver kit, or WDK, has everything you need today. So, recapping. New low-power buses in Windows. We're trying to provide great options for building PCs, and we think we've done that by adding these low-power buses, in addition to our wonderful bus support for USB, USB 3, PCI Express, etc. But we really have a wide variety of buses to accommodate a very wide variety of form factors and systems for system builders, for peripheral makers. We certainly try to make everybody happy. One driver, one part. So let ACPI and Windows handle the plumbing. You guys worry about creating a great part, creating a great driver. And everything you need to get started is in the Windows driver kit, with the exception of that piece of hardware, which Again, stay tuned. Check with us in the coming months. We will be very clear and very loud about how you can get your hands on x86 and ARM hardware with low power bus support. So I went pretty quickly. That is it. I will point you to these related sessions. Architecting and integrating sensor drivers, for those of you who are interested about sensors. We have a whole variety of information about sensors. I believe that's tomorrow. In fact, all of these are tomorrow. It's really great to get up to speed with Visual Studio, knowing that all the driver development for ARM, for x86, for x64, all of that is done with Visual Studio and the Windows Driver Kit. And just an example of one of the many new technologies built on these new low-powered buses is Bluetooth on low-power buses. We also have a variety of information on our website. That contact info is really good to note, too. The simple bus at Microsoft.com email address hits me, hits Peter, hits some of my team members that are scattered throughout the room. Please feel free to send questions. You will reach our whole team, and we can help walk you through any questions you have as you develop a driver. If you're trying to wire something up, if you're a PC maker and want to know how things need to fit together, if you're writing ACPI and you're stuck on some little, error, please use that as an email address, and we will happily help you along. And our job is there to help you guys build great PCs, great peripherals, everything. So that's it. Does anyone have any questions? And if so, can you please just walk up to the question mic so that it can be recorded? Yes?
Is it working?
Is the mic on?
Test,
Hold on.
test.
There it is.
It goes. I believe for Windows 7, WHQL requirements for hardware put Bluetooth on a particular bus. Maybe it's USB. I forget what it mandates. And so is Bluetooth changing for hardware requirements to be on a different bus? And is it possible to have hardware that's compatible for WHQL on both 7 and 8?
I can't talk about the WHQL. For Windows 7, the logo requirements are going to be about the same. I can't talk too much about that. That's not my area of expertise, but if you catch me later, I can refer you to someone else. For Windows 8, absolutely. We are going to be encouraging Bluetooth on a wide variety of buses. While tomorrow's talk with Bluetooth centers on high-speed UART, Bluetooth can and will exist on other buses, and that will be perfectly good from a logo requirements standpoint.
Do you know if that's hardware configurations backward compatible with 7?
That's something that you'll have to ask the Bluetooth talk tomorrow. That's out of my comfort zone.
Okay, thanks.
So, thanks. Thank you.
Hello. My question is about the documentation. I've indeed seen those samples in the WDK, but there's no documentation whatsoever. It basically says it's going to be all on the website, but I would want to see like the SPB interface documentation, for example.
I will check that. It should be on the website. It should be on MSDN and in CHM form.
It's not.
It's not? Okay. Well, I will write that down and find out where it went off to, but thank you. The plan is, though, that it will be fully documented on the website. So. Okay.
Okay, I have a question regarding latency. We have a device which needs to be serviced, let's say in something like 1 millisecond intervals. And I would like to know few related things. One is there any penalty if we use UMDF for that? The second one is, are you supporting a shared SPI where one SPI is shared by multiple devices? And if yes, how do you solve the priority issues? Who talks to that first?
Yes, so we absolutely do allow multiple devices on, I try to answer in two parts. We do allow multiple devices and multiple drivers to use one bus, and it is a first come, first serve. A driver that needs to lock the bus for some period of time can do so. But we don't, it's basically a first come, first serve, and we would ask that drivers be courteous and use interrupts and spend only the necessary amount of time accessing the bus as possible. For the question on latency, the question was, are you asking if 1 millisecond latency is achievable, or what can you, sorry, it was, my hearing isn't great.
If there is any problem with that, and if there is any penalty if we use UMDF for that.
Yeah, Peter might. Do you have a mic, or do you just want to? Here, just hold this.
For UMDF, I mean, there is I don't like to call it a penalty, but there is a cost associated with isolation. 1 millisecond is probably at the edge where you want to do some performance testing and prototyping and see what you can actually pull off. And on the SPI question, I just wanted one quick clarification is we do support shared devices, but it's a single master architecture. We don't support multi-master in this release. So.
In one of those big picture sessions, someone mentioned that there will be a class driver for HID over I²C. Can you tell me more about this? Like, does it mean that I can just create an I²C device, plug it in, and expect it to work?
So you're referring to the HID over I²C class driver? Yeah. So what that looks like, I probably have a picture of what that looks like. We didn't squeeze it into the deck initially. If you look at the SPB accelerometer stack, it's going to look very similar. The HID over I²C is going to look somewhat similar. Now, obviously, this is the sensor driver stack, but HID over I²C is we call it an inbox component. It ships in Windows, and that would be that red part right there. But the upper edge of that is the input stack. Ignore the user mode, kernel mode separation there too. So what you have is those green controller drivers that would come from the silicon vendor, which again, you don't have to worry about, unless I have some silicon vendors in the room right now. But the green part, you don't have to worry about. That will be installed on any device that you would get with Windows 8 on it. And then that red part would really be a blue Microsoft-provided part, which runs into the HID layer. And the upper edges would be the input stack, and that's already in box and ready to go, and all you have to do is implement firmware, and then your manufacturer of the computer has to put the right stuff in ACPI, and that's it. But it's totally there. The only third-party component are those controller drivers, which will be taken care of in advance.
Hello? Hello?
Oh, is that mic?
The mic is on. Hello? Hello?
Mic over there?
Oh, is it?
Try again?
No, I don't see the switch in here. No.
Maybe you can just come over to one of the other mics. Sorry. Lost the game of mic roulette there.
Actually, touch device is a big topic for the Windows 8. So other than the USB interfaces, any driver prepared for the touch devices as a low power device, low power bus point of view?
Can you repeat the question real quick?
The touch device.
Attached device.
No, touch.
Sorry, touch.
Other than the USB drivers,
so touch can be on a variety of buses, but really touch for Windows 8 we're looking at for USB HID and HID over I²C as well. Those are the two.
Oh, I²C was it?
Yeah.
As well?
I²C, absolutely. So these devices that you see up here are all running with I²C.
Oh, okay. Thank you.
So, on many platforms, especially SOC, you don't really have a whole lot of access to USB or PCI. So these low-powered buses are great for system-on-chip platforms that really might have one USB controller, and it would be a lot of power to put in additional hubs. So Yes. So, but please feel free to email questions if you have further ones.
Although they are ARM-based systems.
Yeah, yes.
Yes. Oh.
Yep. Oh, sorry, I've not seen the ordering here.
Yeah. Following on to the previous question about trying to get a compatible connectivity between Windows 7 and Windows 8, is there any intention to port any of this stuff back to Windows 7 in terms of just the low-level interface part of this?
No, there is not a plan to port this back to Windows 7 at this time. There's considerable work in the kernel and in ACPI. So these are all Windows 8 technologies. Now, some of the platform providers, especially x86, obviously, they may have other accommodations as far as providing controller drivers and their own interfaces or interfaces which closely mirror ours. But you should talk to them. But right now, we have no plans to port this backwards for Windows 7.
Hello, I just wanted to introduce myself. My name is John Christensen, and my team actually writes the content for the WDK. And so I just wanted to encourage all of you. We do have a lot of content up there for driver development. I would encourage you all to come by and see us over in Studio D, and we can help you find your way through some of it. And we do have a lot of new content. We'll have a lot more to come in the months to come as well. So, I'm sorry? Oh, well, it's going to be continuous. We don't have like a specific date for each thing. We have a lot of the reference content and a lot of the basic kind of driver overview content is up now. So we'll be writing a lot more guide and procedural and examples in the months to come. Oh, I'm sorry. I'm there most of the day tomorrow, actually. So if you could come by any time. If I'm not there, there's a bunch of other people there as well. Thank you very much.
Yeah, thank you. Hi.
So following up on the question that was asked earlier, you pointed that there are some SoC platforms that you have. What about x86-based platforms and the availability of I2C, or rather lack of it, on them? And
so I don't want to comment on companies' future roadmaps, but for example, all the SoC systems that you can see in that big expo hall, from especially the ones today, I know in the house, there's NVIDIA, Intel, TI, and Qualcomm. The four of them actually have these I2C and GPIO and SPI drivers running inside. This isn't limited to SoC hardware, so I think by the time we see Windows 8 come around, you're going to see a whole variety desktop to I'm going to mess up the terminology if I try to name it all. But you're going to see these buses on a variety of platforms. But as far as platforms you can get your hands on of both architectures, we're looking in a few months, and you'll get news from us. And really, this technology does not distinguish between ARM or x86. It's all the same.
Okay. Another question was that you talked about multiple devices sharing these buses. Again, coming to touch devices, and I mean, there might be certain bandwidth requirements for certain frame rates. And given the importance of touch, how does one make sure that you're getting enough time on the bus?
So that really comes down to testing and smart system planning. We work with OEMs and ODMs and part manufacturers to understand the characteristics of a given part. Obviously, something like touch, if you think of 10-finger multi-touch at a very high sampling rate, that's going to be a lot of traffic. So what we would do is encourage touch to be on a bus that has less traffic on it. Maybe fewer devices, maybe no other devices. And so we work with PC manufacturers to provide that guidance. A lot of this also comes down to testing. For better or worse, the great thing about these buses is that this is not plug and play. This is all inside a sealed piece of plastic, and everything is soldered. So really, at the end of making a device and creating a reference design, you have the opportunity to test everything to, we joke, we shake things around. We have robots that are going to be touching and turning and spinning and playing music and playing video, and you kind of hammer it to understand if the traffic patterns on the buses work. So, there's no hard, clear answer, but you can kind of look at the chatty peripherals and keep them alone, and take a bunch of peripherals which don't require a lot of data, like, say, for example, a bunch of sensors that don't report very often, and throw a lot of them on the same bus.
Thank you.
Okay. Yes. Oh,
Yeah.
sorry. I don't know who's first.
Go ahead.
Okay.
Yeah, can I get the other sample HPI table for supporting the other driver?
Sorry, can you repeat that a little bit louder? My
yeah.
hearing is not so good.
Yeah, can I get the other sample HPI table for supporting other driver?
I can't. Sorry, just a little bit louder. I'm sorry about that. Or
Yeah.
actually, can you ask me afterwards? My hearing isn't so good. Or maybe a little bit louder.
Yeah. Can I get the other sample HPI table?
The other sample ACPI table?
For supporting the other driver?
Oh, sure. Yes, that's something that you should email me. Better to email. Let me make sure not like a salesman. Let me keep that email address back up on the screen. That Simple Bus email address. Email us, and we will help you with ACPI samples, and we can show you how they work. There are some in the WDK. I can't name them off the top of my head, but there are a variety of ACPI samples there. Email us, tell us a little bit about your part. We will also help kind of show you what that looks like.
Yeah, okay,
So we've all become kind of experts in writing ACPI.
Yeah.
Quick question on power management.
Yes.
Like on SPB bus. If you're going to have a device, say like a radio, you want to turn off and on, maybe through a switch on a console versus through your Windows OS, how would that be handled in this model?
Sorry, I missed part of that. Can you repeat that one more time?
If I have an SPB device, like a Bluetooth radio or some other radio on your bus, and I have like a console switch where I can turn on and off the radio directly, either through the BIOS, but not through the OS, driver stack.
Okay.
How do I handle that with your current architecture?
So we would expect a peripheral driver that's controlling that part to manage the power policy, or at least be informed. So if you're going to cut off the power, it should enter a D3 state.
So if you're really cutting the power to the device, it's going to be completely non-responsive. You could modify the firmware to have the device disappear when that switch is flipped. There is a flight mode in Windows 8 that I know nothing about, except that there's a flight mode in Windows 8. But that would probably be the better integration point for such a switch than just cutting the power rail to the radio. And then otherwise, we have the way we have it set up, devices and buses sort of power manage independently. So bus controllers, the controller drivers can power down when they're not in use, even if radios are left on to do their processing. And then they power back up when I/O comes in to try and retrieve data from the device.
Yes.
Okay, one more question. It's slightly theoretical, but the SPI and similar interfaces are primarily used for internal devices, but it could be used maybe by some OEM devices also as an external interface, for example, on an extension connector or something like that. If that happens, how is the configuration handled in that case? Is there some way how software can override the ACPI information in the firmware, or how this would be solved?
So, as we said earlier, these are not plug-and-play buses, for sure. And I know electrically a lot of these buses can't really run that far. It depends on how the system's being designed. But there's lots that you can do in ACPI if you really want to work with a manufacturer and dive into the world of ACPI. One example might be an ACPI method, which can hide and unhide a device. That's a great question. The email is simplebus@microsoft.com, and we could explain that. There's absolutely a world of customization here, and that nearly everything you can think of is possible. Nearly. Don't want to make too many promises. But if you email us, we can help you out with that and give you an idea of who to talk to. But it is possible with ACPI. I can even think of it in my head, where you could hide and unhide a device based on a command, or change the identity of a device. But these are not plug-and-play buses, and primarily should not be. We don't assume that they're treated as such, so we may run into things that we didn't address.
You mentioned earlier that all of the Windows 8 computers, or Windows 8 capable computers, are expected to have an I2C controller in them. And what is the future of the PS2 port in this game?
So I would definitely go back and say that Windows 8 computers may have I2C, may have SPI. These are options that an integrator can use. It's going to totally depend on what type of customer requirements they have, how they want to design the system. We are adding buses to Windows, we're not taking away. So PS2 is absolutely there, it's still there, it can continue to be used. And I know that there are some other talks on, Fred, are there talks on input at this conference? Okay, there's a Chalk Talk tomorrow at 4 p.m. on input. So as, like if you look at a multi-touch touchpad, it starts to exceed the bandwidth of PS2. But we're not saying no PS2. We're not saying you must have I2C. We're saying that there's a lot of options out there. So there's a lot of creative wiring solutions too. Anyone else? Oh, go ahead.
Just wanted to check if you have any comments around SDIO, because it was pretty absent from the slide.
So SDIO, while we're not covering that as a low power bus, it very much is, and I think we're going to see a lot more of that in Windows 8, especially on SOC platforms. I don't know if there are other talks off the top of my head. It's another bus, though, that we encourage as additional options. You're going to see wireless, like Wi-Fi on SDIO. I think if you come talk to me afterwards, I can probably find the right contact or talk for you. But that's out of my domain, and the buses that we were specifically providing new APIs for are.
It does not fall into the simple bus architecture.
No, so SDIO is an enumerable bus, but it may use some simple bus assets, like for example GPIO for power or for like card insertion, or there may be other uses. In fact, a lot of the SDIO parts will use a UART or an I2C side channel for some other sort of sideband communication. But SDIO is an enumerable bus, and it has that advantage, and doesn't need this kind of same plumbing.
Yeah, it's also SDIO provides power can provide power within the bus, so we have a more direct parent-child relationship that we have to maintain for power management. But basically, if you can slap ACPI on the node and add resources into it, then those resources can be used to the resource hub. So as long as it's something that's in the device tree that you're happy to describe in the system firmware, you can do that. I don't think you would use GPIO and SDIO for a plug-in card anyway. It seems a little weird to have an extra line. So.
I just asked Fred, where is that Chalk Talk?
I'll go and catch up with you after. Okay.
One last question. Okay. So from that whole thing, from a device manufacturer standpoint, we only have to write one driver, WCL it, and then everything on the lower layers is provided by Microsoft for all platforms.
Yes. Well, Microsoft and our wonderful third-party silicon vendors, yes.
And with the SPB interfaces, one of the ideas we had was we've seen devices where the same set of registers are exposed either through SPI or I2C, and it's a very small change when you actually do your write register address read, in terms of like maybe you set a bit on SPI and you don't on I2C. And the SPB interface works for both of those. So you have to make a very small change in your communications when you are running over SPI or I2C, but you could actually write one driver. We believe you could write one driver. I think we did this with accelerometer.
Yeah, for this accelerometer part, it has both SPI and I2C, and the driver would work on no matter how it's wired.
Yeah, so we wanted to avoid the world where you have to write two drivers, which would have sort of been an old Windows way to do it, right? And be able to have one driver that can work on your part no matter how it's wired up.
Well, that's it. Thank you for attending. I hope that you guys have all had a great day. Peter and I are still available up here for questions if you want to come and talk to us privately. Otherwise, again, I'll plug, look at the Windows Driver Kit, look at the documentation online, email simplebus@microsoft.com if you have any questions, want to introduce yourself. But I will also be at the Ask the Experts section tomorrow evening. So please come find us either now or then, and have a great time here in Anaheim. Thank you.